Good morning, all the students. Now we'll start our sixth lecture under this module 1. Just tell me if you can see this presentation.
Yes, ma'am.
Okay. Okay, in the previous class, we have understood how concept learning can be treated as a search problem. Because whenever a machine is learning about a concept, it is trying to search the hypothesis space, that is capital H as we represent it. Now, the machine is trying to learn all possible hypotheses from this hypothesis space H. Okay, and it is trying to search for the best hypothesis that can explain, or the best statement that can explain the entire training examples given. Okay, that statement which would fit the behavior of all the training examples given. Okay, so the concept is being searched for, the concept is learnt by the machine from the larger hypothesis space. That is why it is called as a search problem. And we also understood about find as algorithm, and also we have gone through one example which better illustrates this find as algorithm. Okay, what are the steps that are taken up by this algorithm in order to arrive at a more general hypothesis. Now in today's class, we are going to understand about version spaces and candidate elimination algorithm. Version spaces, this term is very important because this will be used hereafter in upcoming chapters. So you should be able to immediately connect with that term whenever it is used in your classes, right? So let us see about version spaces, its representation, the list then eliminate algorithm, very simple algorithm. Okay, all these, the basic concept actually can be explained in a single line. It is that simple. And they are actually poor performers. They don't perform that well, but they are very much essential for us to understand the framework and some basic concepts in machine learning. That is why, though these are not best performing algorithms, in order to understand the underlying concepts and some complex framework of machine learning, we should go through these algorithms: list then eliminate algorithm, find as algorithm, candidate elimination algorithm. All these are very important. And let us proceed to more compact representation for version spaces by using this list then eliminate algorithm, right? And in the next class, we'll see exactly what is candidate elimination learning algorithm, and also go through an example to understand that concept more better. Now, what is version space and what exactly is this candidate elimination algorithm? Although find as outputs a hypothesis from H, we have seen this find as algorithm, right? Now, this find as algorithm outputs a hypothesis from the hypothesis space H that is consistent with the training example. See, I always use this term, consistent with the training examples, means the hypothesis can explain, it will apply to each and every training example, right? Or set of hypotheses. If not single hypothesis, at least we take set of hypotheses which will apply for any training example that is given for the machine to learn from. Okay, so this is just one of many hypotheses from H that might fit the training data equally well. So whenever a find as algorithm is applied and some hypothesis, best fit hypothesis is found, it may be one of several other best fit hypotheses. Means I'm trying to say that there will not be one single solution or one single hypothesis that can explain the behavior of all the training examples, that can apply to the all training examples. The hypothesis that you take can be multiple. Okay, one single hypothesis can't explain everything. So the hypothesis can be multiple hypotheses which would cover the entire set of training examples given. Okay, now in find as algorithm, it may output one single hypothesis or multiple hypotheses, so that it explains the training examples given for training to the machine. Now, the key idea in the candidate elimination algorithm is to output a description of the set of all hypotheses consistent with the training example. Understand this. Again, I'm telling about this consistent with the training examples means whenever you want to perform this candidate elimination algorithm, it starts with more number of hypotheses which will apply to that particular training set, and slowly it will start eliminating the candidates so that it arrives at a more general hypothesis that covers the entire training examples. Okay, so both perform poorly. They don't perform very well, but they don't perform very well with noisy training data. Noisy training data means lots of combinations of parameters. The combinations of parameters doesn't repeat. Sometimes there will be outliers in the training examples. If such, and there will be some missing data or there will be some duplicate data. This is all called noise in the data. Duplicate data, missing data, and outliers in the data are called as noisy data. If the data contains all this, it is called as noisy data. Now, this finders algorithm and candidate elimination algorithm will perform very poorly with this noisy training data if it is given. Okay, but the candidate elimination algorithm, why we are learning about it if it is not performing so well? Why we need to understand about it? Because it provides a useful conceptual framework. It tells us about some fundamental issues in machine learning. It makes us understand some fundamental concepts in machine learning. That is why we need to understand all these preliminary algorithms very well before going forward with advanced algorithms. So that whenever you come across such complex algorithms, topics, you will easily understand what exactly this finders and candidate elimination algorithms have done. Now, how do you represent a version space? Version space is denoted by VS. Now, before going to the representation, let us first understand the difference between a hypothesis consistent with the training example and a training example X satisfies a hypothesis. What is the difference? Now, when I say an instance X is satisfying a hypothesis, then I can represent it as h of x equal to 1. Means this hypothesis is covering that instance of training example. A hypothesis is said to cover an instance of training example X if h of x is equal to 1. Then we say that X is satisfying the hypothesis H, right? But what is consistent? Consistent means if the hypothesis on an instance, a hypothesis on an instance of the training examples, if it is equal to the concept that is learned by the machine, means if it is according to the target concept, that is all the positive examples, then we say that that particular instance is that particular hypothesis is consistent with the target concept, or it is consistent with the hypothesis. Both are same, right? H of x equal to C of x. I'll repeat this once again, do not get confused. If I say an instance training example X is satisfying a hypothesis H, then we denote it as H of x equal to 1. In this case, it just sees whether that hypothesis covers the training instance. It doesn't bother about the outcome, whether it is yes or no. Okay, so it is just trying to satisfy, the instance is trying to satisfy the hypothesis. Okay, whether the outcome is yes or no, whether the outcome is 1 or 0, it is not worried about that. But if I say that a hypothesis is consistent with the target concept for the training example given, then we represent it as h of x equal to C of x. In that case, the machine is highly interested in the outcome variable, whether it is yes or no. Outcome label, whether it is yes or no. In that case, If you take the positive examples, then we say that the hypothesis is consistent with the training example X. I'm repeating this. Whenever we say that a hypothesis is consistent with X, then the outcome variable should be a positive training example. It should be S. Outcome label should be S. Okay. Now the candidate elimination algorithm finds all the describable hypotheses that are consistent with the observed training examples. So when I say consistent with the observed training examples means all the outcome labels are equal to S only. Only those examples will be taken in order to formulate a hypothesis, right? Let us say that a hypothesis is consistent with the training examples if it correctly classifies these examples. Okay, this is another understanding. Let us say that a hypothesis is consistent with the training examples, means in accordance with the training example, if it correctly classifies these examples as positive or negative. Okay, and it is interested only in positive examples, not in negative examples. Now, based on this knowledge, let us try to understand the formal definition of what is consistent. A hypothesis H is consistent with a training example, is consistent with a set of training examples D if and only if H of X equal to C of X. Now go back to the definition of satisfying with finders. There they have given an instance X is said to satisfy a hypothesis H if and only if H of X is equal to 1. That is the definition given there. You can go through the previous PPTs. Okay, but here when we are trying to understand what is consistent, it is nothing but the hypothesis is in accordance with the target concept. That is whether your friend is enjoying the sport. Yes, it is interested only in S, positive examples. Now see this definition again. A hypothesis H is consistent with a set of training examples D. It contains all the training examples X1, X2, X3, right? If and only if H of X is in accordance with the concept, that is C of X, means wherever the outcome is only S. Okay, for each example, understand it more better. For each example, X is set of all combination of parameters, and C of X, that is the outcome variable, outcome label S or no in D in each training example. How it is defined? Consistent H of D means H hypothesis is consistent with D. You should read this like this. This term, you should read it as H is consistent with D. I'm repeating again. You have to read this term as H is consistent with D. And that is equivalent to, how is it defined? How you define consistency of H with D? For every training example and its target label that is belonging to the set of training examples, means what we are meaning here is a valid training example. That's all. Okay. For every training example that belongs to the set of training example, H of X, the hypothesis, should be in accordance with the concept that is being learned by the machine. What is the concept being learned by the machine here? Whether your friend will enjoy the sport, and it is interested in S. That is only positive examples. Then we say that H is consistent with D. Now I'll read this last line once again. H is consistent with D is defined as or is equivalent to this representation that for every training example that belongs to the set of training example D, such that H of X, that is hypothesis, is equal to the concept that is being learned by the machine. Then we say that H is consistent with D. Got it? Now the candidate elimination algorithm represents the set of all hypotheses consistent with the observed training example. Candidate elimination algorithm, how it starts? It starts with set of all hypotheses. It doesn't start with a single hypothesis, right? It starts with the most possible number of hypotheses, and it tries to eliminate those hypotheses in order to arrive at a final hypothesis that better explains the training examples, and that could generalize well to the unseen examples, right? So this subset of all hypotheses is called the version space. Understand this clearly. Now, whenever you write all the hypotheses possible for a training example set, then that set is called as version space. Okay, this subset of all hypotheses is called the version space with respect to the hypothesis space H and training examples D. These two terms are very important. We are defining a version space with respect to the hypothesis space H and the training examples D because it contains all plausible versions of the target concept. All plausible means all applicable, all reasonable versions of the target concept. Got it? So whenever you take the set of hypotheses, they should be in accordance with the training examples that it has come across. There should not be any hypothesis which doesn't apply to any of the training examples. Okay, that is what is the meaning lying behind this explanation. The hypothesis space H contains all hypotheses which are consistent with the training examples in the training example set D. If there is any hypothesis which is not according to the training examples or which is not consistent with the training examples, then we say that that hypothesis doesn't belong to the hypothesis space at all. It doesn't apply to any of the training examples. Okay. Now, what is the definition of version space? Again, a formal definition is given here. The version space denoted by, see, this is very important, this representation. In the last class, we have seen a representation more general than, right? Now, we should remember this version space representation. The version space, with respect to, you should read this term as version space with respect to hypothesis space H and the training examples D. Okay? I'll say once again, you should read this term as version space with respect to the hypothesis space H and the training examples D. Okay? Is the subset of hypothesis from H consistent with the training examples in D? That is what I have been explaining so far. Now, how you can mathematically represent this? Version space, whenever you are reading it after the class, you always read this without any laziness. You just read this as version space with respect to hypothesis space H and training examples D is defined as or is equivalent to any hypothesis that is belonging to the hypothesis space H given that H is consistent with D. How nice it is, how beautifully it is represented. All this entire definition is given in a single line. So I'm trying to read this line once again. You follow carefully. Version space with respect to hypothesis H and training examples D is defined as or is equivalent to all hypotheses belonging to the hypothesis space H such that what type of hypothesis it should be? Such that H is consistent with D. Means the hypothesis space capital H should contain only those hypotheses which are consistent with D. It should not contain any other hypothesis which are not consistent with the training examples given. Got it? Now let us see a simple algorithm, the list then eliminate algorithm. The list then eliminate algorithm first initializes the version space to contain all hypotheses in H, then eliminates any hypothesis found inconsistent with any of the training examples. Means this algorithm starts with a finite set of hypotheses that it can define on the training examples. Right. Now it has given all the possible hypotheses. Now this version space is checked one after the other. Okay. Now whenever a hypothesis is in accordance with the training example, retain it, keep that hypothesis. But if a hypothesis H is not found to be consistent with the training example, means there is a hypothesis but it is not covering a particular training example, then you have to eliminate that hypothesis, because it is not useful to retain that particular hypothesis in the hypothesis space. Okay, if insufficient data is available to narrow the version space to a single hypothesis, then the algorithm can then the algorithm can output the entire set of hypotheses consistent with the observed data. What do we mean by this? If at all more number of training examples are not given, in that case, this algorithm doesn't know which hypothesis doesn't apply to which training example. In that case, it has to output the entire set of hypotheses consistent with the observed data so far. Okay, that is the output given by this list then eliminate algorithm. So this works only for finite hypothesis space. Remember, if there are infinite number of hypotheses in the hypothesis space, you can't apply this algorithm because it involves more number of iterations in order to eliminate the hypothesis that doesn't apply to the training examples. So you have to take the finite set of hypotheses for any given problem. If it is applicable, you can take only finite set of hypotheses and start eliminating each of them whenever it doesn't apply to the training example. Okay, I'll give you an example. Say initially in H you have H1, H2 and H3. You have started with this finite set of hypotheses. You have listed down this set of hypotheses according to the knowledge that you preliminarily have about the training examples. Okay, that is the fundamental knowledge. From the fundamental knowledge that you have about the training examples, 3 hypotheses are listed. Okay, this forms the hypothesis space H. Now these hypotheses are checked with each of the training examples. For this training example, H1 is consistent with, and with this training example, H2 is consistent. With this training example, no hypothesis is consistent. With this training example, H2 is consistent. Okay, now all the training examples are gone through. H3 doesn't cover any of these training examples. So remove that H3 from the hypothesis space. In the next iteration, try to search for other training examples. In the next iteration, more and more training examples as they are given to the machine, it tries to eliminate the hypothesis based on the training examples encountered. So what will happen here? If you give more number of training examples, the hypothesis space will shrink. It will generalize to 1 or 2 hypotheses. But if you give very few examples, then the hypothesis space will have more number of hypotheses because it can't learn properly which hypothesis will generalize. So it will try to output H1 and H2 in this case, but no more training examples are given. So it doesn't know which one to select, H1 or H2. So it keeps both of them. Okay, that is the example of this list then eliminate algorithm. It starts with all possible hypotheses and tries to eliminate the hypotheses that are not consistent with the training examples, and it refines more better as and when more training examples are given. Now the list then eliminate algorithm can be applied wherever the hypothesis H is finite. If it is infinite, this will take lots of iterations in order to arrive at a general hypothesis. So better apply this only with finite hypothesis space. Now let us see a more compact representation of this version space, how we can more smartly define this version space. Candidate elimination algorithm works on the same principle as list then eliminate algorithm, right? Even in candidate elimination algorithm, all the candidate hypotheses are taken. Now, whenever a hypothesis is found to be inconsistent with some training example, that is eliminated from the hypothesis space, right? So CE employs a much more compact representation of the version space, right? Candidate elimination algorithm is actually more compact and precise, more clear representation of this version space. In particular, the version space is represented by its most general and least general members. Means what? In version space, you will have only the most general hypothesis and the least general hypothesis. Least general, how I can call it in a different way, as specific hypothesis. Least general hypothesis means more specific hypothesis. Least general member means most specific member. Okay, so in particular, the version space has two members. One is the most general hypothesis and one is the least general hypothesis, means more specific hypothesis. Now let us see this list then eliminate algorithm. A version space, initially what it contains? A list containing every hypothesis in H, all possible hypotheses in H. Now, in the second step, what will happen? For each training example, X and its label C of X, that is the target concept, yes or no. X is combination of all the parameters, C of X is the label. Okay. Now, for each training example, X and C of X, remove from version space any hypothesis H. When do you remove? For which H of X is not equal to the target concept, means wherever the output label is equal to no, you try to remove that particular example. You try to remove that particular training you try to remove that particular hypothesis which explains that training example, because your machine is trying to learn only the target concept S. It is not interested in the instances where the target label is no. That is why whenever a no is encountered, all that entire hypothesis which explains the training examples attribute combinations, that entire thing have to be removed. Means that hypothesis is removed. That is how at each iteration you try to reduce the number of hypotheses in the hypothesis space. Now you repeat this again and again. Finally, what will be the output? The output, the list of hypotheses in the version space, the remaining hypothesis in the version space. And all these hypotheses now are consistent with the training examples given. Nice it is. Initially you start with every hypothesis. Every hypothesis means every training example is covered by each hypothesis. H1 will cover day 1 data, H2 will cover day 2 data, H3 will cover day 3 data, and H4 will cover day 4 data. Right? Now, in the third example, you remember in that your friend, whether he'll enjoy the sport or not, some data is given with the training examples. Now, in that the third day data, outcome label is no. So that hypothesis H3 will be removed. And as and when it goes through, if at all there is any target label as no, that particular hypothesis will be removed. And the final hypothesis space will have all the hypotheses which are consistent with the training examples where the target label is S. Now that hypothesis space is called as version space. Now let us see figuratively how this version space can be defined. Version space will contain the boundary hypothesis. Boundary hypothesis means most general hypothesis and most specific hypothesis represented by G and S respectively. Okay, so what is the general hypothesis here? There are two general hypotheses. One is sunny, rest all, any value is allowed for the attributes, and other generalized hypothesis is for the sky attribute, it allows any value, but it is very specific about the next attribute. It should be warm, and other attributes can be any. Okay, these two are general hypotheses. Now you can see these arrows. These arrows will represent more general than or equal to representation, notation. Okay, these arrows will indicate that this G is more general than any of these hypotheses given. Right? So this hypothesis, sunny and strong, it has extra one constraint on strong. So it is more specific than G. Here it has extra constraint on sunny. So it is more specific than G. And here it has extra constraint as strong. So it is more specific than G. Now, you go further and see the most specific hypothesis, it has more constraints than this middle level, right? Sunny, warm, and strong. So this is called as the most specific hypothesis. This is the boundary for the most specific hypothesis, and this is the boundary set for the most general hypothesis. Right? So this most general hypothesis boundary set contains all the generalized hypothesis, and most specific boundary set contains all the specific hypothesis, one or it can be many also. Okay. Now let us understand those two definitions of general and specific boundaries. See this definition, the general boundary G, that is your last line in the figure, with respect to hypothesis space H and training data D, is the set of maximally general members. Remember this term. Whenever you're writing this definition, you have to underline this term. Maximally general members of H consistent with D, and how it is defined mathematically. Understand this carefully. I'm reading this mathematical representation. I'm not just denoting the terms. I'm trying to read this. That will make you understand what exactly is this representation. G, the general boundary, is defined as all the general hypothesis that belongs to the hypothesis space H such that given G is consistent with the training examples, that is general concept, right? And there is a conjunction and there should not exist, this is negation of exists. So it is there should not exist any G dash that belongs to H, means there should not be any other generalized hypothesis that belongs to H such that G dash is more general than G. Means G should only be the maximum generalization of the hypothesis. Okay, so there should not exist any G dash that belongs to the hypothesis space such that G dash is more general than G, and G dash is consistent with D. I'm reading this once again. The general boundary G is defined as set of all generalized hypotheses that belongs to H given G is consistent with D, and that G is only should be the maximum generalized hypothesis, and that is explained in this part of the definition. There should not exist any G dash that belongs to the hypothesis space where G dash is strictly general than G. Got it? Strictly more general than G, and G dash is consistent with D. Means there should not be any hypothesis G dash which is consistent with D and is more general than G in that hypothesis space. Only then it is called as the general boundary. Yes, if at all you don't understand in this first instance, read this again and again. You will clearly understand. Okay, I want only G. I don't want any G dash that is more better than G. That more better generalizes than G. That itself is the definition. Okay, now let us see opposite of this, contrary to this. Contrary means the definition opposite. Okay, the specific boundary S with respect to hypothesis space H and training data D, same till here. Now, what is the specific boundary defined as? Is the set of minimally general. Here it is maximally general. Here it is minimally general. Minimally general means maximally specific. Maximally general means minimally specific. These two are these two can be used complementarily. Means they can be exchanged. So in this definition, I can tell it as minimally specific or maximally general. In this definition, I can say as minimally general or maximally specific. So entire representation will be the same, except here you are taking the specific hypothesis than general hypothesis. Okay, so maximally specific members of H consistent with D. And how is this boundary, specific boundary set defined as? It is the set of all specific hypotheses that belongs to the hypothesis space H, given all these specific hypotheses are consistent with the training examples, and there should not exist any specific hypothesis that belongs to H such that it is more specific than the existing specific hypothesis, such that S dash is consistent with D. Means there should not exist any specific hypothesis that is more specific than what is existing in this specific boundary set. Then only we can call this as the final specific boundary set S. This specific boundary set S should contain all the specific hypotheses which are consistent with the training examples, and this should not contain any more better specific hypotheses that are better than this hypothesis in this specific boundary S. Okay, that is what we mean. It should not contain anything better than what is existing. In that case, we say that that is maximally specific or that is maximally general. Now, what is the theorem that is represented by this version space? We can define a theorem like this, version space representation theorem. Let X be an arbitrary set of instances, means random set of sample. It can contain any day's data. If we take that friend enjoying the water sport example, it can contain some days set of data. Next time when a different sample is taken, it can contain different set of days of data, right? So we call it as arbitrary set, random set. Now let X be an arbitrary set of instances, and let H be a set of Boolean valued hypothesis with outcome as 0 or 1 defined over X. That is the set of all training examples. Let C be mapped from the instance set to 0 and 1. What is the concept? It is trying to learn whether your friend will enjoy the sport S, that is 1, or 0, that is no. Okay. Now let C be an arbitrary target concept. Why we are saying it as arbitrary? It may be refined later as and when it encounters more training examples. Okay. let C be an arbitrary target concept defined over the set of instances X, and let D be an arbitrary set of examples of all the training examples, that is X and C of X. Now, for all X, that is the set of instances, for all H, that is the set of hypotheses, for C, that is the concept, target concept that is being learned, and D, the set of training examples, such that S and G are well defined, means generalization boundary and the specific boundary, both are well defined. Most general hypothesis boundary and most specific hypothesis boundary, both are well defined. Then how does this version space definition change? Version space with respect to the hypothesis H and the set of training examples D, how do you define that? It is set of all hypotheses that belongs to the hypothesis space H given what is the condition? There exists a specific hypothesis that belongs to the specific boundary, and there exists a general hypothesis that belongs to the general hypothesis boundary. And now what is further condition? G, that is general hypothesis, should be more general than any of these hypotheses, and this should be more general than any of the specific hypothesis. That is what is mentioned, right? This G is more general than this intermediate hypothesis. Three hypotheses are there, right? That is H, and that is more general than this final S. That is what is defined. Though there are 6 total hypotheses here. See, in general hypothesis set you have 2 hypotheses. In H you have 3 hypotheses. In S you have 1 hypothesis. Totally 6 hypotheses you have. But in the version space you will have only G and S. Means it will be reduced to 3 hypotheses from 6 hypotheses. That is called as the version space. You will not have all the hypotheses, but you will have the boundary hypothesis for general hypothesis and specific hypothesis. Now you see this finally once. Version space with respect to hypothesis space H and the training examples D is defined as the set of all hypotheses that belongs to the hypothesis space H such that there exists a specific hypothesis that belongs to the specific boundary set, and there exists a general hypothesis that belongs to the general boundary set, and also this general hypothesis should be maximal when compared to H, means more general when compared to H, and H should be more general when compared to specific hypothesis in the boundary set S, capital S. Okay, this is how we define the target, this is how we define the version space with this theorem 2.1 that is given. Okay, go through this theorem, you will easily understand from the explanation given. Now in the next coming up session, let us discuss candidate elimination learning algorithm and more understand it more elaborately by using an illustrative example. Now quickly I want answers from you. What is G? One answer. Just one answer. Simple, crisp answer is required. I'm now
general boundary form. General
what is
boundary.
G?
General boundary.
Yes, yes. General boundary set. Very good. Apurva and who else? Okay, I'll see in the video. When you have spoken, your icon will come. I'll check it later. So G is general boundary set. What is H? Others, I want to answer. Sorry, I want them to answer.
Hypothesis.
Hypothesis. Space. H is hypothesis space, which contains number of hypotheses. Okay, all possible hypotheses. Small h under capital H. So this H is called as hypothesis space. G is general boundary set, as you said. H is hypothesis space. Okay, what is S? Students, what is S? When you are able to tell what is G, S is also similar to that, right? What is S?
Specific boundary, ma'am.
Yes, specific boundary set means it should contain all the specific hypotheses. Okay, what is X?
Random set of instances.
Very good. Random set of instances. What is small x?
All random set of
X is each and every instance. Capital X is set of all the instances. Small x is each instance. What is C? What is C? That is very important, right? That is how you know that a hypothesis is consistent with the target concept. What is C? I already told you the answer.
consistent data.
No, no, no. C is target concept. Target concept that it wants to learn, whether your friend will enjoy the water sport or not. So the target concept it is trying to learn is S, whether he is interested, whether he is enjoying that sport. S. It is not interested in no instances. It is interested only in S instances. What is small h?
Hypothesis.
Very good. Hypothesis. What is D?
A training example, ma'am.
Set of training examples. What is VS?
Version space.
Yes, version space, which contains the most general hypothesis and the most specific hypothesis, right? Okay. So in the next class, we'll learn about candidate elimination algorithm. Any doubts still here, students?
No, ma'am.
Ma'am.
Is it very clear?
Yes, ma'am.
Yes,
Yes, ma'am.
yes. You can join for your next class. Bye.
Yes, ma'am.